Just to recall what we have discussed in our last class. We have discussed algebraic extensions, and we have proved every finite extension is an algebraic extension, etc. And the last problem we have discussed is find basis of q of root 2 root 3 over q. Now moving to next problem, show that q of 2 raised to 1 by 2, 2 raised to 1 by 3 equal to q of 2 raised to 1 by 6. Okay, so actually what is q of 2 raised to 1 by 2, 2 raised to 1 by 3? It is the smallest field containing q 2 raised to 1 by 2 and 2 raised to 1 by 3. What is q of 2 raised to 1 by 6? It is the smallest subfield containing q and 2 raised to 1 by 6. Okay, now as it is 2 raised to 1 by 3, note that 2 raised to 1 by 3 is a root of x cube minus 2, and x cube minus 2 is irreducible over q. Therefore, irreducible of 2 raised to 1 by 3 over q is x cube minus 2, and degree of 2 raised to 1 by 3 over q is 3. Clear? Therefore, degree of q of 2 raised to 1 by 3 over q is equal to 3, which implies that q raised to 2 raised to 1 by 3 is a three-dimensional vector space over Q by theorem 29.24. Just recall theorem 29.24. This is equal to f of degree of f of alpha over f equal to n implies f of alpha is an n-dimensional vector space over f. We have that result. Using this result, we get q of 2 raised to 1 by 3 is a three-dimensional vector space over Q. So what about the basis? Basis element consists of f of alpha consists of basis 1 alpha, alpha square, etc. alpha raised to n minus 1. So here dimension 3, therefore 1 alpha, alpha square. Okay. Here alpha is 2 raised to 1 by 3, degree 3. So 1, 2 raised to 1 by 3, 2 raised to 1 by 3 square. Degree 3, n minus 1 means 3 minus 1 equal to 2. So here 2 raised to 1 by 3 and 2 raised to 1 by 3 whole square. That is 1, 2 raised to 1 by 3, 2 raised to 1 by 2 by 3 is a basis of q of 2 raised to 1 by 3 over q. Okay, that is here 2 raised to, here this is actually 2 raised to 1 by 3 square. Okay, and that's equal to 2 raised to 2 by 3. Now consider root 2 because 2 raised to 1 by 2. Irreducible of root 2 over q is x square minus 2, and degree of root 2 over q is 2. Okay, and we have a result. If beta belongs to f of alpha, then degree of beta over f divides degree of alpha over f. Okay, but 2 does not divides 3. Degree of beta over f divides degree of alpha over f if beta belongs to f of alpha. Here degree of root 2 over q is 2. 2 does not divide 3. Therefore 2 raised to 1 by 2 does not belongs to q of 2 raised to 1 by 3. Okay, but 2 raised to 1 by 2 belongs to q of 2 raised to 1 by 3 of 2 raised to 1 by 2, and which is equal to q of 2 raised to 1 by 3 comma 2 raised to 1 by 2. We have alpha belongs to f of alpha. Here 2 raised to 1 by 3 we replace q of 2 raised to 1 by 3 as f. We get 2 raised to 1 by 2 belongs to f of 2 raised to 1 by 2. Okay, so and this f is q of 2 raised to 1 by 3, and that comes this one. Okay, now irreducible of 2 raised to 1 by 2 over q of 2 raised to 1 by 3 same as x square minus 2, because this is clearly a polynomial over q, and 2 raised to 1 by 2 does not belongs to q of 2 raised to 1 by 3. Okay, therefore x square minus, we cannot factorize this one. Okay, therefore irreducible of 2 raised to 1 by 2 over this is equal to same as x square minus 2, and its degree is 2. So q of 2 raised to 1 by 3, 2 raised to 1 by 2 over q of 2 raised to 1 by 3 is equal to 2. because degree is 2, and therefore what about the bases? Bases consist of only two elements, that is 1 and 2 raised to 1 by 2. So 2 raised 1, 2 raised to 1 by 2 is a basis for q of 2 raised to 1 by 3, q of 2 raised to 1 by 2 over q of 2 raised to 1 by 3. Okay, so now this is the basis of q raised to 2 raised to 1 by 3 over q. Now we get like this: q raised to 2 raised to 1 by 3, q of 2 raised to 1 by 3, and q. Here basis is 1, 2 raised to 1 by 3, 2 raised to 2 by 3. Now this one, q of 2 raised to 1 by 3, 2 raised to 1 by 2. Here basis is 1, 2 raised to 1 by 2. So what about the total basis? Basis of q of 2 raised to 1 by 3, 2 raised to 1 by 2 over q is, multiply each term, we get this one. Okay, that is 2 raised to 1 by 3, 2 raised to 2 by 3, 2 raised to 1 by 2, etc. Now from this 2 raised to 7 by 6, you can write as 2 into 2 raised to 1 by 6. Okay, therefore 2 raised to 7 by 6 clearly belongs to q of 2 raised to 1 by 2, 2 raised to 1 by 3, which implies 2 raised to 7 by 6. Okay, okay. Now 2 raised to 1 by 6 is a 0 of x raised to 6 minus 2, which is irreducible over q. Okay, now by existence criteria with a p equal to 2, we get like this: q is a subfield of q of 2 raised to 1 by 6 is a subfield of q of 2 raised to 1 by 2, 2 raised to 1 by 3. Okay, therefore degree of this equal to q of 2 raised to 1 by 2, 2 raised to 1 by 3 over q of 2 raised to 1 by 6 into q of 2 raised to 1 by 6 over q. Now q raised to 2 raised to 1 by 6 over q is 6, and q of 2 raised to 1 by 2, q raised to 1 by 3 over q is 6, because 1, 2, 3, 4, 5, 6. Okay, now this value is 6, this value is 6, and this value is also 6. What about this value? This value is 1. This implies this one. We have f of e over f, degree of e over f equal to 1 implies e equal to f. Therefore q of 2 raised to 1 by 2, 2 raised to 1 by 3 equal to q of 2 raised to 1 by 6. Okay, now here we have one result. Here you have to replace this like this. Now 2 raised to 7 by 6 equal to 2 into 2 raised to 1 by 6, and 2 raised to 7 by 6 belongs to this one, which implies 2 raised to 1 by 6 belongs to this one, because 2 is already there. That means this product also belongs to this, means 2 raised to 1 by 6 also belongs to q of 2 raised to 1 by 2, 2 raised to 1 by 3. Okay, now moving to next problem. Let f of x belongs to capital F of x and f of x be of degree 2 or 3, then f of x is reducible over f if and only if it has a 0 in f. We have already discussed this problem. Anyway, proof is this: suppose f of x is reducible over f, then f of x you can write as g of x into h of x, where degree of g of x and h of x are both less than degree of f of x. Since f of x is either quadratic or cubic, either g of x or h of x is of degree 1. Okay, because this is cubic polynomial means like this. Factorization means, and some you can write as x minus a into x minus b into x minus c, or you can factorize this as some x square minus something into some x minus, okay, like this. So in any factorization you will get a polynomial of degree 1. Then either g of x or h of x is of degree 1. If g of x is of degree 1, then except for a possibility is factors in f. Okay, so g of x, suppose g of x is of degree and then g of x is of this form, x minus a. Okay, and then g of a must be equal to 0, which implies f of a equal to 0. So f of x has a 0 in f. Okay, so now conversely, suppose that f of a equal to 0, then clearly x minus a is a factor of f of x. So f of x is reducible. Okay. Now moving to next theorem, let E be an algebraic extension of a field F, then there exists a finite number of elements alpha 1, alpha 2, etc. alpha n in E such that E equal to this one. So we have already proved every algebraic extension need not be a finite extension, but we have one result. Let E be an algebraic extension of a field F, then there exists a finite number of elements alpha 1, alpha 2, etc. alpha n in E such that E equal to f of alpha 1, alpha 2, etc. alpha n if and only if E is finite dimensional vector space over F. If you can write E as f of alpha 1, alpha 2, etc. alpha n, then E must be a finite dimensional vector space over F. That is if and only if E is a finite extension of F. Therefore, if E is an algebraic extension, then if E, you can write some alpha 1, alpha 2, etc. alpha n and f of E as f of alpha 1, etc. alpha n, then E is a finite extension. Similarly, if E is a finite extension, then you can write E as there exists alpha 1, alpha 2, etc. alpha n in E such that this condition holds. Suppose E equal to f of alpha 1, alpha 2, etc. alpha n. Since E is an algebraic extension of f, each alpha is algebraic over f. This implies each alpha there exists a polynomial f of x belongs to f of x such that f of alpha equal to 0. If K is any extension field of f such that f of alpha is a subfield of K of x, okay, suppose K is any extension field of f, then clearly because f of alpha is the smallest field containing f and alpha, okay, this is a subfield of K of x. Now hence f of x belongs to K of x, which implies that alpha is algebraic over K, because this polynomial f of x, here f of x, here this is actually f of x. Then if K is any extension field of f, then f of x is a subfield of K of x. Okay, but because every polynomial in f of K of x have coefficients from f, and every element in f is in K. Therefore, this element in also belongs to K of x. Hence, f of x belongs to, thus given any alpha I algebraic over f means it is algebraic over K. Hence, each alpha I is algebraic over every finite extension field of f in E. Hence, by theorem 13.3, alpha belongs to E is algebraic over f. Alpha belongs to E is algebraic over f. If degree of alpha over f is equal to n, then f of alpha is an n-dimensional vector space over f. Okay. Okay. Here we have okay. Now by theorem 13.3, okay. F of alpha is an n-dimensional vector. Now this implies alpha 2 is algebraic over f of alpha 1, which implies f of alpha 1, alpha 2, because each alpha is algebraic over extension field. Okay. Here we have alpha I is algebraic over. Now we prove alpha is algebraic over extension field of f. So from this f of alpha 2 is algebraic. Alpha 2 is algebraic over f. Using this result, alpha is algebraic over f and alpha is algebraic over every extension field of f means alpha 2 is algebraic over f of alpha 1, because f of alpha 1 is an extension field of f. So alpha 2 is algebraic over f of alpha 1. Therefore f of alpha 1 alpha 2 is a finite dimensional vector space over f of alpha 1. Because this is algebraic over f. Okay, f of alpha 1. Now that is f of alpha 1 alpha 2 is a finite dimensional vector space over f of alpha 1. Now alpha 3 is algebraic over f implies alpha 3 is algebraic over f of alpha 1 alpha 2. So f of alpha 1 alpha 2 alpha 3 is a finite dimensional vector space over f of alpha 1 alpha 2. This process is repeated. Okay, finally we get f of alpha 1 alpha 2 etc. alpha n is a finite dimensional vector space over f of alpha 1 alpha 2 etc. alpha n minus 1. So using this finally we get, okay, sequence of finite extension. Then apply corollary 31.2. That is f is a subfield of k is a subfield of E implies E is a f is a subfield of E is a subfield of k implies k is a finite extension over f if and only k is a finite extension over E and E is a finite extension over f. Apply this result, we get E is a finite extension of f. Okay. Conversely, suppose that E is a finite algebraic extension of f, and we have to prove that E you can write like this, f of alpha 1 alpha 2 etc. alpha n for some alpha I. Now if E over f is equal to degree of E over f equal to 1, then clearly equal to f, which is same as f of 1. Now suppose E not equal to f, then there exists a alpha 1 belongs to E1 such that alpha 1 not belongs to f. Then f of alpha 1 is a finite dimensional vector space over f, and f of alpha 1 over f is equal to degree of f of alpha 1 over f is equal to is strictly greater than 1, because if it is not equal to 1, because alpha 1 not belongs to f. If f of alpha 1 over f equal to 1 implies f equal to f of alpha 1, that means alpha 1 belongs to f. That is a contradiction. Therefore f of alpha 1 over f must be greater than 1. If f of alpha 1 equal to E, then we are done. If not, choose an alpha 2 belongs to E such that alpha 2 not belongs to f of alpha 1. Then alpha 2 is algebraic over f. Therefore it is algebraic over f of alpha 1. Therefore f of alpha 1 alpha 2 is a finite dimensional vector space over f of alpha 1. Therefore f of alpha 1 is finite, and this is greater than 1. If this is equal to E, then we are done. Otherwise you repeat this process, and finally we get like this. Okay, and we know that the right members in the right are finite, and finally we reach as a point such that degree of E over f is finite, and we arrive at an alpha n such that f of alpha 1 alpha 2 etc. alpha n is equal to E. Now moving to next theorem, next session, algebraically closed field and algebraic closures. Now first theorem, this is important. Let E be an extension field of f, then f E closure equal to set of all alpha belongs to E such that alpha is algebraic over f. Okay, is a subfield of E, and it is called algebraic closure of f in E. What is f E closure? F E closure is set of all alpha belongs to E such that alpha is algebraic over f. So what we know as what this one, QC closure, set of all alpha belongs to C such that alpha is algebraic over Q. Okay, that is set of all algebraic numbers. So we have to prove this, and sometimes it may ask prove that QC closure is a subfield of. Okay, so in that case you can replace F by Q and E by C. Now Fe closure is like this, and beta belongs to, we have to prove that it is a subfield. That means if you take any two elements, addition closed, multiplication closed, like this, inverse exist, etc. Beta belongs to Fe closure, beta is algebraic over F, and for every element of Fe closure is algebraic over F. Okay, therefore Fe closure is an algebraic extension of F. If you take any alpha comma beta belongs to Fe, then by theorem 31.16, f of alpha beta is a finite extension of f. Since every finite extension is an algebraic extension, f of alpha beta is algebraic over f. F of alpha beta is contained in Fe closure. Note that f of alpha beta is the smallest subfield of E containing f, alpha and beta. Therefore, since it is a field, alpha comma beta belongs to f of alpha beta implies alpha plus beta, alpha minus beta, alpha by beta. For beta not equal to 0, all are in f of alpha beta. That means all are in Fe closure. Therefore, Fe closure is a subfield of E. Prove that set of all algebraic numbers form a field. If you take C as a set of all complex numbers and over Q, then this is actually QC closure algebra. Okay, sorry. Yeah, it's same QC closure. Algebraic closure of Q in C. Therefore, by above theorem, it is a field. Therefore, set of all algebraic numbers form a field. This is important. Okay, so prove that set of all algebra. For that, you have to write previous theorem. Okay. Now, this definition, from this definition onwards, we will discuss in our next class. Okay, that's all for today's class.